Hello everyone, and back again. So my apologies, I kind of skipped this here, the derivation of the bias variance trade-off, because I thought it's maybe too theoretical and maybe something not everyone is interested in. Obviously it's important to understand the concepts, but maybe the mathematical derivation is maybe only accessible to some of you and might be not so interesting to others. But I forgot that I had put an exercise actually into to discuss this and kind of work through the figure which we saw in the lecture in detail. So so let me just kind of go through the derivation very quickly. As I said earlier, kind of the bias variance trade-off, we can only write this down theoretically once we know the actual distribution of the data. If we do not know the underlying distribution of the data, we can only really look at the train error and the test error, but we can't see this difference. But let's just assume that we know the underlying distribution and we can calculate expectation values. So just let's look at the picture there. And again, most important is that we get the notation right. So let's just imagine we have a given point here. So we have x0, it's our point, and at this point x0, what do we have? We have the theoretical line. I wrote this as a dashed line. So the theoretical line here, this would be the value f at x0. Now, if we sample a data point, we also get a data point y. So this would be just y, or let's call it y0, which would be the data point here which we observe. Now we know that the difference between the two, so we know that y0 is just equal to f of x0 plus epsilon. So this difference here is just epsilon. But now we also know that we had a prediction. So we had fitted some function, and this function might be this one here. Now this point here would be the value of our prediction, which would just be f hat of x0. So f hat would be the fitted function. So kind of f hat of x0 would be, say, our predicted intercept plus some predicted slope times x0 in the case of a linear regression, say. So here we have all the points. We have y0, which is the sample point, f of x0, which is the true point, the different being the error epsilon, and then we have our predicted value f hat. So now when we want to calculate the error, we want to compute the expectation value of the difference between y0 minus f hat of x0 squared. So let's just check what are we calculating here. We want to see how different is our predicted point from the actual point. So this is this difference here. Let's just use a different color. This difference here is what we are looking at, and we are squaring it. So this will effectively give us our error. So we predict this value, f hat, and the actual value was 0. If we kind of square this and then we take the expectation of is, we will get the error term. So this would be our error we are afterwards. And now we want to decompose it. Now to decompose it, the way to do it is we kind of add and subtract terms. So here we can, for example, just go and we add to this, we have y0, and we now start adding and subtracting f of x0, the true value. This is a value we don't know. That is why in general we can't do this decomposition. So we have f of x0, which we subtract, and then we add it. So this changes nothing, and then we still have the minus f of x0 hat, which we had before, and the whole thing squared. Okay, now we just didn't do anything. We just added and subtracted the same term, so nothing has really changed. But now we can kind of decompose the square. We can take this term here and we can take this term here, and we know that this, like a plus b squared, will be like a squared plus b squared plus 2ab. So what we get out of here is the first term here which will just be, let's just write first, so this term here would be just y0 minus f of x0 squared. I put maybe a squared bracket around. And then the second term squared, which would be expectation value of f of x0 minus f hat of x0 squared. And that's it. So why is that it? Because there's a cross term, but the cross term will be a term which multiplies the first term, but the first term is just epsilon. So this term here is just epsilon here. So actually, if I get the cross term, which would be just epsilon times the second term here, epsilon times this term, but because they're independent, I can take the expectation value independently, and I know that the expectation value of epsilon is 0, because my error has mean 0. The error around my observations is mean 0. That's why this cross term, the 2ab, will be 0. So I'm only left with those two terms, and there's no cross term left. And now we have already seen the first term here is just the expectation value of epsilon squared. But this is just the variance here. So the first term will just give us variance of epsilon here. This is the first term. So this is already the first term in our bias variance trade-off. But now we still have the second term flying around. Expectation value of f of x0 minus f hat of x0 squared. Now, for this term, we do the same game as we just did. We decompose it further, but now by kind of adding and subtracting yet another term. So what we now add and subtract is the expectation value of f hat, because obviously our prediction is also now a random variable, because the data is random, so our prediction f hat will also be random. So you can think a little bit of it if you do Monte Carlo simulations. If I now sample some new data, I will get a different prediction. If I now sample some new data, I will get a different prediction. So f hat is also random with respect to the underlying distribution. So I can now look at this term and I can basically add and subtract it. So let me just write this down, the variance of epsilon. This is what we have here. And now for the second term, I will write the expectation value, and now I do a similar trick as above. I do f of x0 minus, and then I will subtract the expectation value of f hat of x0. Then I will add back again the expectation value of f hat of x0, and then I had minus f of x0 hat. So now nothing has changed. And this is still the same expression as above. But now I can do the same trick as before. I will group those two terms, and then I will group those two terms, and I will resolve this square. So I will have a plus b squared, which will be a squared plus b squared plus 2ab. And the cross term will be 0 again for a similar reason as before. So I'm just left with those two individual terms, the a squared plus b squared. And if I write it out, so I have the variance here still, so let me just give different color. So this is just equal to the variance here, variance of epsilon, but now this term here squared, this is just f minus expected value of f hat. But this is exactly the definition of the bias. So the kind of expected value of f of x0 minus expected value of f hat of x0, this thing squared, this is just the bias squared. Because this is, the bias means there's a difference between the true value and what I get in expectation for my for my prediction, and this difference is just defined as a bias. So bias is just the difference between the true value and the expectation of the predicted value here. And the second term, this last term, let's write it in green. This will just be the expected value of f hat of x0 minus the expected value of f hat of x0 squared. But this is nothing else than, this by definition is just the variance of f hat of x0. And just recall that the first term is also called the irreducible error. So I have decomposed my error, which is the difference between the true observation, the difference here between the true observation and my prediction. I took the difference, I squared it, and this is my error, and I've decomposed it as the variance of epsilon, which is the irreducible error, plus this other term, which is the difference between the true value and the expected value of my prediction, and this is just the bias, and this term is squared, plus the last term here. So the last term is just the variance of my prediction. So this is the variance term, and now we have basically all terms together. We have shown that my error here, so this up here is just error. My error is just a combination of irreducible error, bias term, and variance term, where the bias is just the difference between the true value and the predicted value, and the variance is the variation of the prediction. And now this variation might be different to understand, but it's kind of the variation with respect to the true distribution. In practice we never know the true distribution, but if you could simulate from data like we do in the exercise, you would obtain this expression using Monte Carlo simulation. It's a bit like sampling new data, which you can think of getting a new test set. It's a bit like sampling new data from the distribution. This is the whole idea of test set. It's basically, I want to calculate this expectation value. So how can I calculate an expectation value if I do not know the true distribution? I can just sample from the data. So how do I sample from the data? How do I sample new data? Well, I can leave some data out at the beginning and just pretend that it's new data sampled. And this is basically how the test error comes about. So test error is effectively just trying to compute this expectation here by sampling new data. And in reality, rather than sampling new data, which I can't, I will just leave out some data at the beginning, which I pretend is my newly sampled data there. And now I've decomposed the whole thing as a irreducible error, the bias term squared, and the variance here. And hopefully this figure should clarify the notation and should help you also when you do the exercise.